Hello, everyone. We're going to go ahead and get started on section 7.4, which is going to be on compound interest. So as an overview, over long periods of time, simple interest is not really a great deal to investors. You're only gaining interest on your original amount, even if the money in your account is actually going to be much higher after a certain period of time. When interest is computed on the principal and all previously earned interest, we call this compound interest. So you have a little clip here. We say, sure, 2% interest may not seem like a lot, but it's compound. If you invest $1,000 now in just 10 short years, you'll have about $1,219. So compound interest isn't a magical force. I'm just going to try to make more money. So compound interest will earn you more money over time, although it's not going to be a magic force like how they say there, but it will earn you more money over time, especially the more money that you invest and the higher interest rates that you do have. So that's what we're going to learn about in this section, as opposed to simple interest, which we learned in our last section. We're going to do a quick example to kind of demonstrate this idea. You invest $5,000 for 3 years at a rate of 8%. What is the amount of simple interest? So we'll go ahead and we'll use our simple interest formula. We'll have our values, which we want, which is principal, the rate, the time. Our principal being 5,000, our rate 0.08, remember decimal, and time in 3 for years. And our interest, our simple interest formula is interest equals principal times rate times time. So we're going to multiply these values together to get interest is equal to 5,000 times 0.08 times 3, which is equal to $1,200. So the interest after 3 years that you would gain, the simple interest would be $1,200, which is pretty good. So what if we invest $5,000 for 3 years at a rate of 8%? And what if the amount of simple interest is calculated each year instead? So in this case now, we're going to calculate simple interest each year using our new principal and see how much it's going to be at the end of year 3. So for year 1, we have our original principal, 5,000, our rate is 0.08, and now time is 1, because we're just doing 1 year in this case. So our amount, which we had our formula for A, is equal to the principal times 1 plus rate times time. So give us our new amount at the end of year 1. So we plug our values in. A is equal to 5,000 times 1 plus 0.08 times 1, which gives us the value of $5,400. So for simple interest after the first year, we would have $5,400. Now what we're going to do when we go to year 2 is we're going to treat this final value from year 1 like our principal in year 2. So for year 2, our principal is now $5,400. Our rate is still the same, and we're still just doing this for 1 year. So rate, R, and T are the same. We have A, our amount is equal to principal times 1 plus RT, which turns into 5,400 times 1 plus 0.08 times 1, which gives us $5,832. So now on our last year, year 3, we'll use this value as our new principal. So in year 3, our principal is now $5,832. Our rate is 0.08, time is 1. We use the same formula again to have our amount after year 3 be $5,832 times 1 plus 0.08 times 1. And that leaves us with $6,298.56. So we know that if we calculated simple interest over these 3 years, we would have gotten $1,200. That was from our last question. Now here we see that there's going to be a difference of $1,298.56. So just a little bit shy of $100 extra. And this is calculated each year. With compound interest, you can calculate multiple times a year. That will always earn you more money. In this case, we were a little bit shy of $100, so maybe it's not that big of a deal to you. Maybe it is. Either way, it was still more money. So we can see that the more time that we kind of recalculate interest during a specific period of time will earn us more money. And that's the idea behind compound interest. So developing and using the compound interest formula, our formula being A equals P times 1 plus R over N to the power of N times T. A is the amount after T years, equal to your principal times 1 plus your interest rate per year divided by the number of times you're going to compound per year, all to the power of N, the number of times interest is compounded per year, times T, which is your number of years. So this is our formula that we use to calculate compound interest. What we did in our last example where we compounded like every year, that's not what we typically are going to do. It was just an exercise. When we want to calculate compound interest, this is the formula that we will use. You don't have to calculate every year or every month and then add them all together at the end or anything. So compound interest is compounded or recalculated. It can be annually, which is once a year, semi-annually, which is twice a year, quarterly, which is 4 times a year, monthly, 12 times a year, or even daily, which is 365 days a year. One that's missing in here is weekly, which would be 52 times per year, although that's not as common of a compound interest time frame. But it is still accurate. Weekly would be 52 times per year for 52 weeks in a year. So that's how we're going to use our compound interest formula. Let's go ahead and try it. We're going to calculate the following situations using the compound interest formula. For part A, we're going to find the compound interest amount. So in this case, the interest amount for a $7,000 loan compounded quarterly for 5 years at a rate of 3%. Then B, we'll find the amount after 6 years for an $11,000 loan compounded daily for a rate of 5%. So starting with part A, finding the interest amount, meaning that when we use our formula for compound interest, we get our amount after T years. That's the result. So if we want the interest, what we need to do at the very end is to subtract our original principal from the amount that we gained over that specific time period. That'll be how much interest we got. So we want to keep that in mind. But we can set up a couple things first. Our principal is going to be $7,000. Our rate is 0.03 for 3%. Our time is 5 for 5 years. And our N value, the number of times we compound per year, is going to be 4 because we're compounding quarterly. Quarterly would be 4 times a year. So we go ahead and we plug this into our formula. A, the amount after, in this case, 5 years, is going to be our principal times 1 plus R over N to the power of N times T. So putting this all together, this should look like A is equal to 7,000 times 1 plus 0.03 over 4, all to the power of 4 times 5. Now let's go ahead and go over how we put that in our calculator. All right, so we have our starting value, our principal, which was 7,000, is going to multiply our entire situation here. So times, we want to have some parentheses. It's going to be this whole entire result. Now I have 1 plus a fraction, and then that's going to have an exponent on that. So I'm going to give an extra set of parentheses for what is going to kind of be taken into consideration with the exponent. So I have 1 plus, and now I'm going to have a fraction, which couldn't hurt to put in another set of parentheses. So I have 0.03 divided by, in this case, 4. So I finish off the parentheses for my fraction. Then I finish off the parentheses for that whole statement. Then I'll give my exponent and finish my final parentheses. So if you have an exponent, which is going to be this little caret button right here is our exponent. And we have things being multiplied in the exponent's place as well. It's 4 times 5. Finish off our exponent. And our last parentheses for this entire statement, which we're going to multiply by 7,000. So we'll go ahead and see what that equals. $8,128, and it looks like about 29 cents. We would typically going to round that 8 up to 9. And remember, this is 2 decimal places. We're talking about money, so 2 decimal places, smallest thing we can have is 1 penny. So round to 2 decimal places, and that's going to be our answer. So let's go ahead and go back and write that down. All right, so we know our answer, and there we have it. So we said our value here after this amount of time was $8,128.29. But what we see here is that we want to calculate our interest. Our interest being the amount after a certain period of time minus the principal. So we're going to go ahead and subtract 7,000 from $8,128.29 to get our final answer of our compound interest amount being $1,128.29. So that finishes up part A. We can go on to part B. So part B, we want to find the amount after 6 years for an $11,000 loan compounded daily at a rate of 5%. So we can figure out our values that we're going to use, our principal being $11,000, our rate in this case being 0.05, the time being 6 for 6 years, and N, the number of times you compound per year, will be 365. We're going to do it daily, so we're not really considering leap years or the fact that there's technically a quarter of a day every year. We're just going to use 365. So that's how many times we're going to compound per year. So let's go ahead and set this up into our formula. So we have our formula, A is equal to P times 1 plus R over N to the power of N times T. So our amount after, in this case, 6 years, will be equal to 11,000 times 1 plus 0.05 over 365, all to the power of 365 times 6. So let's go ahead and plug that in our calculator again. All right, so we still have our problem from A up there, so we're going to follow along with how we did part A, making sure that we have all the right parentheses and whatnot. So we have 11,000 times, have our sets of parentheses here, 1 plus, now we have another set of parentheses for our fraction here, which is 0.05 divided by 365. Finish off those parentheses. And then we finish off our statement with our 1 plus our fraction. Then we have our exponent. So we use the little caret button there for our exponent. And our exponent is going to be 365 times the number of years, which we said was 6. Finish off our exponent and finish off that whole term. Then we'll press enter, and there we have it. We have $14,848 and what looks like 14 cents. If, remember, the number after the 4 was 5 or higher, we would round up. If it's lower than 5, then we stay the same. So there's our answer. Let's go ahead and write that down. All right, so here we have our answer. The amount after 6 years should end up being $14,848.14. So we calculated a couple situations using the compound interest formula, and we showed how to put that in our calculator. So moving on, we can solve for a new idea as well. We can find the time needed to reach an investment goal. So in this case, this is trying to find the value of t within the equation that we had. So in order to find how long it would take you to reach an investment goal, we'll need to use some new formulas and buttons on our calculators. So we're going to learn very quickly about the logarithmic function. We'll just use it in this case. So the logarithmic function, we say let a be a positive number and a is not 1. Shouldn't be an issue for us when we do our problems. The logarithmic function of base a, denoted by the word log with a small a a little bit below, a little to the right there, we call that log base A, is defined by log base A of y is equal to x, where you're going to use the same values from your exponential equation, a to the power of x equals y. So if you have an exponential equation that looks something like this, you're going to take your values of a, x, and y and turn them into a logarithmic function with the values in these places. So technically we say log base a of x is the exponent to which your base a must be raised in order to give your result. So this is what we're going to use when we need to find the time needed to reach an investment goal. Remember, in our equation for compound interest, t is in the exponent's place. And this will be the only way we can take it out of the exponent's place. So we have to use logarithms. In addition to that, we'll also have to use the change of base formula. We use the change of base formula to change a logarithm with an undesirable base into the quotient of two logarithms with the same desirable base. Now in our calculator, we can calculate logarithms, but we can only calculate logarithms of base 10 or base e, where e is the exponential number. In our class, we're going to focus on log base 10. And most of these times here, we will not end up with log base 10. We'll have to rewrite it so we can use log base 10. Because in that way, we can use our calculators. So what we would do to change the base is if we have log base b of a, we can change this to be log base, whatever we want, of a divided by log base, whatever we want, of b. So we'll always use log base 10 in our case. We can use that in our calculator, and we're going to show how to do that. But these are the two things that we'll need whenever we need to find the time needed to reach an investment goal. This will be the only way we can actually solve for t, which is time. So let's go ahead and try it. As an example, you want to save $5,000 before buying your first new car, and you have $3,000 right now to invest at 3% interest compounded monthly. How long will you have to wait in order to buy that new car? So let's go ahead and go over to our notes to work on this problem. All right, so here's our example. We want to use our compound interest formula to help us solve this. We also want to remember how to change logarithm into an exponent. So we'll leave kind of the things that we need up at the top. So we have our compound interest formula. Then we can have log base a of y equals x can turn into a to the power of x equals y. Then we want to use our change of base formula as well. So our change of base tells us log base a of b can be turned into log base, in this case we're using 10, of a divided by log base 10 of b. All right, I had the original b and a switched in the logs. I did switch those back, and this is the correct format that we're going to use. So here are the three formulas that we're going to use throughout our problem. So let's go ahead and just start with identifying what we do have in our problem. We're told that we want to save $5,000 before buying the new car. So that means that after how much time that we're waiting, I want to have $5,000 at the end, meaning that that's my amount that I want after my specific amount of time. So my A value will be 5,000. And I have $3,000 right now. So that'll be my principal. I want to invest at 3% interest. So my rate, changing from percent to decimal, would be 0.03. And then lastly, compounded monthly. So N being equal to 12 for 12 times in a year. How long will we have to wait? We're trying to find T. That's what we're going to try to find. So let's go ahead and set up all of our information into our formula. This will give us 5,000 is equal to 3,000 times 1 plus 0.03 over 12 to the power of 12 times t. This is our current formula. We want to try to simplify this. We remember that we can solve for our exponent if we have something in the form of ax equals y, or a to the power of x equals y. I don't quite have that yet. We have 1 plus 0.03 divided by 12 to the power of 12 times t, but I've got a 3,000 in the front. And if I can get rid of that, then I'm closer to having that a to the power of x equals y. So let's go ahead and divide each side by 3,000 to get rid of the value in front of our exponential expression. So we'll divide each side by 3,000. And we'll rewrite our problem. We have 5,000 divided by 3,000. We don't need to put this in a decimal. It's actually better if we leave our answer as a fraction and convert everything into decimal at the end. So we'll leave it as a simplified fraction. They're both being multiplied by 1,000, so really 5,000 divided by 3,000 divided by 1,000 for each really just leaves us with 5 over 3. So 5/3 is equal to our expression. Now we had 1 plus 0.03 over 12. We'd really like for that to be a number, not really, a number plus a fraction. We want that to be a whole number. So we can go ahead and calculate what that's going to be. We can calculate what is 1 plus 0.03 over 12. That answer is going to end up being 1.0025. That's what 1 plus 0.03 over 12 is. And then we have our exponent, 12 times t, which is really just 12t. So now what we have here is more of that situation. A to the power of x equals y. So we can use our formula for our logarithm there at the top. I have the right format. I want to turn this into a logarithm. So when I turn this into my logarithm, I will write log, L-O-G, then it's base A. My A value in this case is 1.0025. So log base, I'm going to put some parentheses around it just so we know it's one whole base. 1.0025. Finish some parentheses there. And then it's log base y. So, or log base A of y. So our logarithm has this base, and I'm taking this logarithm of our result, which we said was 5 over 3. And this is going to get some parentheses as well. And this is equal to x, which is whatever's in the exponent's place, which in our case was 12y. 12t, my bad, 12t. So we have log base 1.0025 of 5/3 is equal to 12t. We'll try to solve for t. So now what we have here is a log with a pretty weird base. And if I want to use my calculator, I need it to be log base 10. That's what I can calculate in my logarithm. Or that's what I can calculate in my calculator with logarithms. So we have log base 1.0025 of 5/3. So we're going to go ahead and use our change of base formula. That is at the top. That's our last formula we haven't used yet to rewrite our logarithm. So for here, we'll use change of base. So when we use our change of base, what we really have here is log base b of a. That's what we have. And we're going to use what we know it's equal to rewrite it. So we said log base b of a is the same thing as saying log base 10 of a, which is 5/3, divided by log base 10 of b, which in this case was 1.0025. And we're still stating that this is equal to 12t. So now we've rewritten this. It's a very important thing to note at this point that log base 10 is commonly just written as log, and not log base 10. So an important note we're going to do right here, log base 10 is really just log without a base. So whenever we see log without a base, we always get to assume that's log base 10. And when we get to put this in our calculator, the button on our calculator just says log, which inherently is going to mean base 10. So we can drop the base 10s at this point because we've established that log base 10 is really just log without a base. So whenever you see log without a base, it means base 10. All right. Then we're trying to solve for t. T is being multiplied by 12, so we can divide each side by 12. So let's write out our final statement here. We have t is equal to, we have log of 5/3 divided by log of 1.0025. And that whole thing is being divided by 12. So we're going to go ahead and plug this in our calculators. We're going to see what this equals. So let's go to our calculator now. All right, so we're going to learn how to use our logarithms in our calculator. So before we start, we want to identify where the log button is. It should be right here. It has the words log. That means log base 10, which is why we want to change everything to be log base 10. So this is our log button. So whenever we use log, this is where we're going to use it. All right. So we know our formula. We said it was going to be log of 5/3 divided by log of 1.0025. And all of that will be divided by 12. So we want to make sure that we have some parentheses around what needs to be calculated first, which is the top portion. So we'll have a parentheses. Then we're going to do log. And you see when you type log, it comes with a parentheses, meaning that you have to finish them off. So we have log, and now we have 5/3. So log of 5/3 divided by log of 1.0025. So one more set of parentheses. This finishes off our logarithm statement here. And then remember, we're dividing this all by 12. Press enter. We get 17.048799634. So we have quite a few values there. We're going to go ahead and round to the nearest whole number, which in this case we have 17.048. Technically, the 8 pushes the 4 to a 5, and the 5 would push the 0 to a 1. But if we're just rounding to the whole number, that's going to be 17 years. So let's go ahead and write that as our final answer. So here we are in our work. We plug this into our calculator, and we said, rounding to the nearest whole number, this would be equal to about 17 years. So the question is, you want to save $5,000 and you currently have $3,000 and you're going to invest at 3% interest compounded monthly? You're waiting 17 years to buy that car. You should probably just find another way to make some more money. So, all right, that finishes up that example. Let's go on back over to our lecture. All right, so picking up where we left off, now we're going to talk about effective rates. So the effective rate, which is also known as the annual yield, is the simple interest rate which would yield the same future value over 1 year as the compound interest rate. So effective rates lets us compare different compounded rates by putting them into a simple interest rate instead. So it lets us compare with the different compounding years and months, weeks, days, all that kind of thing. So we're going to look at our effective rate interest. So calculated using the following formula, we have E, the effective rate, is equal to 1 plus R, the interest rate per year. This could also be called the stated rate or the nominal rate, divided by N, the number of periods per year the interest is calculated, all to the power of that same value of N minus 1. This will give us our effective rate. Remember, working with rates, so when we get an answer and it's in decimal, we'll need to convert it over to percentage. So we're going to go ahead and try some of this out. Our example here, which savings account do you think is a better investment? We have 6.2 compounded daily and 6.25% compounded semi-annually. So we're going to use our formula from our previous slide there, and we'll identify some of our values. So for part A, starting off, we have our rate, 6.2%. To decimal, it's going to be 0.062. And we're compounding daily, so 365 times a year. And we'll use our equation. We said our effective rate E is going to be equal to 1 plus R over N to the power of N minus 1. So plugging all of our values in, we get E, our effective rate, is equal to 1 plus 0.062 over 365 to the power of 365 minus 1. So let's go ahead and put that in our calculator. All right. So starting off with our 1 plus R over N to the power of N. So starting off with some parentheses, of course, we're going to have 1 plus, we're going to put some extra parentheses around our fraction. 0.062 divided by 365. Parenthesis rounds off our fraction. Another parenthesis rounds off everything in there in those parentheses. Now we're going to do to the power of 365. Now we want to make sure to subtract 1 minus 1. We'll press enter. We get this value. 0.063956748. We don't want to write all those values. We're going to go ahead, we're going to round. Let's do 2 decimal places for our percentage, which really means 4 decimal places in our decimal. So 4 decimal places would be the 0.639. So let's look to the next number. The next number is a 5, which will kick up the 9 technically to 10, which kicks up the 3 to a 4. So really, this would be about 6.40%. So we can go ahead and put that in our notes. So we see our effective rate E would be about 0.06395, which turns into about 6.40%. So our effective rate for 6.2% compounded daily in simple interest would be about 6.4%. So all right, let's check now our 6.25 compounded semi-annually. So we're going to see which one is the better investment. So our rate in this case is going to be 0.0625, because now we have 6.25 as our percent. And compounded semi-annually means twice a year, so N would be 2. Putting that into our formula, we have E, our effective rate, is equal to 1 plus R over N to the power of N minus 1. So E is really 1 plus 0.0625 over 2 to the power of 2 minus 1. So let's go ahead and put it in our calculator. All right, so when we calculated part A, kind of missed an extra set of parentheses. We typically want one going to be around our exponent so that the minus 1 comes last. Luckily, our calculator still reads it in that form, so our answer was still correct, but it's always good to have everything very clear. So we'll go ahead and do it the other way. We'll add in that set of parentheses. Our answer is still calculated the same, luckily, but we want to make sure to keep everything very organized. So we have 1 plus, and in this case, we're going to go ahead and put in our fraction. So plus 0.0625 divided by 2. So we have everything within our parentheses to the exponent of, in this case, 2. And then we'll close off those parentheses. So all of that will be calculated, and then we will subtract 1. We get our answer, 0.0634765625. So just like last time, we're going to round off to 4 decimal places in this case. So we have 0.0634. The next number is the 7. So 4 technically goes up to a 5. So this would really be 0.0635, which we can turn into a percentage to make 6.35%. Let's go ahead and put that in our notes. So our value here, we have E is equal to about 0.0634. The 7 can technically also go up to an 8 in this case, but either way, it comes out to about 6.35%. So we have our percentage here. So our effective rate for 6.25% compounded semi-annually converted into simple interest is 6.35%. For 6.2 compounded daily in simple interest, that gets converted to about 6.4%. So which savings account is a better investment? 6.2% compounded daily is the better investment. That's the higher interest rate there for your savings account. Now, if this were calculating loans, you would definitely want the lower interest rate, but since it's a saving account, we want to make better money, then 6.2% compounded daily would be the better rate. So, all right, there's using our effective rates. So we can go ahead and move on. Now we have annuities. An annuity is a savings investment plan where an investor makes a regular fixed payment into a compound interest account where the interest rate doesn't change during the term of investment. This differs from a regular compound interest account in that you don't invest an entire amount at the beginning of your investment period. You break up the investment into smaller payments. So for an annuity, you're paying into your account at a specific periodic time, as opposed to compound interest. Compound interest is just a lump sum that gains interest. An annuity, you pay into that every so often. The total amount accumulated, payments plus interest, is ending up called the future value of the annuity. These are very common used in retirement plans where you pay into them as you work throughout your life so that when you retire, you have a lump sum that has been gaining interest since you've been working. So this is how typically annuities are going to work. They do have different formulas for this as well, since you're constantly putting money into it as opposed to just a lump sum from the beginning. So here's our formula for finding the future value of an annuity. We have A, the future value of the annuity, is equal to capital R. So now we have two values of R in this case. So capital R is the regular periodic payment. Then we have 1 plus little r over n, our annual interest rate, divided by the number of payments made per year, all to the power of n, number of payments made per year, times t, which is the term of the annuity in years, minus 1. That all goes in the numerator, and that's divided by little r, the annual interest rate, divided by n, the number of payments made per year. So this is our entire formula here for the future value of an annuity. And if you've realized it yet or not, you'll have to be very careful putting this into your calculator. This is a much longer, more complicated equation. It becomes very important to remember your parentheses. So, all right, let's go ahead and look at a quick example. You open an annuity with semi-annual payments of $800 at 5% compounded semi-annually for 4 years. What is the future value? So just as every other time, we're going to start off by saying what our values are going to be. Our regular payment, is $800. Our rate is 0.05. N would be 2 because we're talking about semi-annually. And T would be 4 for 4 years. So we're going to go ahead and plug that into our formula. Now remember our formula, A was equal to capital R times 1 plus little r over n to the power of n times t minus 1 all over little r over n. So plugging in our values, we end up getting our future value is equal to 800 times 1 plus 0.05 over 2 to the power of 2 times 4 minus 1 all over 0.05 over 2. So this is our formula. Let's go ahead and look over how to put it in our calculator. All right, so it's very important to keep everything very clear and organized. So our first set of parentheses will be for our numerator in general. So in our numerator, we're having 800 times a bunch of stuff. So start with the 800 times and a new set of parentheses. This new set of parentheses will take into consideration our 1 plus our fraction and our exponent minus 1. The first thing we want to do, though, is put in our fraction, 1 plus 0.05 over 2 all to the power of 2 times 4. So we'll give another set of parentheses to input that. Then we want to make sure that our exponent goes inside the right place. So we're going to give it one more set of parentheses. We'll have 1 plus our fraction 0.05 over 2, which is by itself. Now we have that entire statement to the power of 2 times 4. Finish off our exponent. Finish off that statement. Now we have our minus 1. That wraps up that part of our chunk there. And that wraps up our numerator. Then we're going to divide by our denominator, which is a fraction, so another set of parentheses, 0.05 divided by 2. And we'll go ahead and find that value. So the future value in this case would be $6,988, and it looks like about 89 cents. So that should be the future value of our annuity. So by paying in $800 twice a year, compounded at 5% for 4 years, at the end of our 4 years, this is the value that we should end up having. All right, let's go ahead and go over to our notes. So we calculated our answer, which was $6,988.89 in our annuity. So, all right. Moving on, let's do an example altogether. So here we have, you've dreamed of opening your own tattoo parlor and you decide to do it. A financial planner estimates that you would need about a $35,000 initial investment to start the business, and you plan to save that amount over the course of 5 years by investing into an annuity that pays 7.5% compounded weekly. How much would you need to invest each week? So for this case, for this problem, we're asking, how much are you investing each week? That's corresponding to that value of capital R, the value of the periodic payment. So we know for our annuity, we solve for future value. Now we have to solve for the periodic payment. So we're going to see how we do that. So let's go over to our notes so we can work on this problem together. All right, so for our example, we're going to go ahead and rewrite our equation here for the future value of an annuity. Remember, we want to know how much we need to invest each week, which is going to correspond to the value of R, capital R, to be specific. So we need to go ahead and figure out how to solve for that. So R, we know, is right here. And so we want to be able to simplify it so that it's by itself, it's isolated. So our first step in being able to do that would be to multiply each side by what's in our denominator, R over N. If we multiply each side of our function by R over N, it will cancel on the side where we have R, giving us A times R over N is equal to capital R times 1 plus little r over n to the power of n times t minus 1. Now we have that r is being multiplied by all of this value here. That value there is being multiplied by r. So if we want to get rid of it, what we have to do is divide both sides by that term. So we'll divide by 1 plus little r over n to the power of n t minus 1. We have to do that to both sides. So we'll divide 1 plus little r over n to the power of nt minus 1. Now on the right-hand side, since I'm dividing by the same value, those are going to cancel themselves out. Finally, giving the equation, r is equal to a times little r over n, all divided by 1 plus r over n to the power of n times t minus 1. So this will be our formula for how much we'll need to pay, in this case, per week. So with using this formula, we have our values that we're going to use. We have A should be 35,000, R should be 0.075, T will be 5, and N will be 52 for 52 weeks in a year, and our investment will be weekly. So we'll take all these values and plug it into our formula for R. So R will be equal to 35,000 times 0.075 divided by 52, all divided by 1 plus 0.075 over 52 to the power of 52 times t, which is 5, minus 1. That'll be our entire denominator. So we know what our formula is. We're just going to go ahead and plug it into our calculator to find what our weekly payment should be. Remember, we're talking about money, so we're going to round to 2 decimal places when we get our final answer. So let's go ahead and put this in our calculator. All right, so just like before, we need to be very careful when plugging in these values into our calculator. We want to make sure we're very organized and have parentheses in all the right places, or else our calculator can give us an incorrect answer. So let's go ahead. When we put in our numerator, first we want to make sure that that is all good to go within its own set of parentheses. So we have 35,000 times. Now we have a fraction, so we'll put another set of parentheses, and this will be 0.075 divided by 52. Finish off the parentheses for the fraction, finish off the parentheses for the numerator. So we finished our numerator, which was the easier part. Now we're going to do our denominator, which is the messier portion. So we have parentheses for our entire denominator. Then we're going to have parentheses for our statement with an exponent. And then we'll have another parentheses for what actually goes inside the parentheses that has the exponent. So we'll have 1 plus. Now we have a fraction, so we'll put another set of parentheses. 0.075 divided by 52. Finish those parentheses. Then we finish that fraction, so we finish what's inside the parentheses. We have an exponent of, in this case, 52 times 5. Finished our exponent. Now we want to finish that whole statement. Then we have minus 1. And finish off our denominator. So we'll go ahead and find that value. This should give us about $1,100 and 0.047655. What we see here is that we should be rounding to the second decimal place for cents, of course. And we see the number after that is a 4. The number after that is a 7. Technically, the 7 kicks the 4 up to a 5, and the 4 kicks up to a 5 as well, technically. So what we're going to do is we're going to have $111.05. As we see, those values are going to increase up to 5 cents instead of up to 4 cents. So that's what we'll have as our answer. When it comes to things like this on the exam, it's always important to do your best to round, but it does have a tolerance, so within a certain percent range, a couple cents off shouldn't really make that much of a difference. But all right, so let's go ahead and write our final answer in our notes. All right, so we had our answer, $111.05. That would be our answer on how much we would have to save per week. So, all right, that finishes up our example. So now if you ever have to do a problem like this again or a similar problem, you can always remember this is the formula for how to find how much you need to pay into an annuity per week. So you can always rearrange the formula to find out something else that's not necessarily what your formula is set out to find, but you can always rearrange it to find another version. So, all right, that wraps up that example. Let's go on back over to our lecture. All right, we finished up our example, and that wraps up section 7.4. So in 7.4, we learned how to develop and use compound interest formulas, find the time needed to reach an investment goal, compute the effective interest rate of an investment, compare the effective rate of 2 investments, find the future value of an annuity, compute the periodic payment needed to meet an investment goal. So, all right, that finishes up section 7.5, and I'll see you in the next one.